The Lynch motor is a unique design of axial gap permanent magnet brushed EC electric motor. The motor design has a flat pancake dash-like appearance, and was invented by Cedric Lynch from 1979 a circumflex onwards, with the relevant patent filed on 18 December 1986. The design, components and tooling was slowly improved, mainly by Cedric, but also with a lot of input from Richard Fletcher and his project team at London Innovation, including William Reed, from 1985 to late 1992. London Innovation Network financed the patents and the building of early prototypes, including a batch made by Aerosoft Engineering, which incorporated some ideas used in subsequent motors. Around 1989 onwards, Lynn had been searching for a company to manufacture the motor, having already successfully made small batches and individual units, like the motors used in the Countess of Arran's World Electric Boat speed record attempt in 1989, those motors being assembled by Cedric Lynch, with help from William Reed, who assembled armatures in his hospital bed after a car accident. Hotek's wet Trevelise worked was one of the companies approached, and after Cedric showed them how to make the motor, they declined to manufacture it. Instead, Trevor left them in January 1993 and joined the Lynch Motor Company as factory manager on a salary to assist Cedric Lynch and Lynn in setting up larger-scale production, using tooling previously developed and new tooling designed by Lynch, some of which was made by a local toolmaker Roger Cox. The motor was developed into a full production item primarily by Cedric Lynch and this small team, and manufactured by the Lynch Motor Company Limited as the Lynch motor. After a rift developed between Lynch and Lynn and the Lynch Motor Company in late 1996, the intellectual property was held in Lynch IP, with Lynn having 50% rights and the Lynch name, and a new company was formed, Lamco, who had the other 50% of the rights. This consisted of J.P. Hansen Group main shareholder, with Cedric and Trevelise as small shareholders. Cedric Lynch joined the Indian company Anai Motors in 2002, where it is built and sold as an iMotor. A further licensed design was made by Briggs & Stratton as the Etic DC motor. The latest model of an iMotor is manufactured and distributed by Sayeta Group, which has been formed following merger of Agility Global and Anai Motors in May 2015. The motor design achieves an electrical efficiency of over 90%. It is built using iron ferrite blocks sandwiched between strips of metal instead of traditional copper coil windings, and is held together purely by the strength of the magnets within it. The design given a nominal continuous output of around 15 horsepower in a package weighing 11 kilograms. The traditional Lynch motor design has a spinning armature held on a spindle between two banks of 8 fixed permanent magnets. Also stationary are 8 brushes on the front side which allow electric current from the power source to reach the armature. The design of the Lynch motor armature is significantly different compared to other types of motor. The armature coils are formed from insulated copper strips, each in a U-shape. One leg is then bent 45 degrees clockwise, while the other leg is bent 45 degrees anticlockwise. Each coil leg contains several bends before reaching the outside of the armature to be able to pass radially through the ferrite ring before the ends finish 90 degrees apart. At the outer edge, each copper strip has a crimp forming an electrical connection to its companion 90 degrees rotated. The inner edge of the copper strips have the insulation removed on the front face only, to form the commutator surface, where the brushes make contact. Between each copper coil leg are placed the pieces of the subdivided and insulated iron ferrite cores making up the ferrite ring. The ferrite ring carries the magnetic flux between the fixed permanent magnets, without needing to use the copper strips. As the armature spins, current flows from the one brush into the commutator, outwards along one copper coil leg, which is sandwiched between the iron ferrite core pieces. When the current reaches the connecting crimp positioned on the outer edge, it transfers to a new leg on rear side of the armature, and runs back to the center, again sandwiched between ferrites 45 degrees out of phase from the previous ferrites. The electric current then arrives back at the center, 90 degrees later, and swaps sides back to the front face, before reaching the corresponding brush 135 degrees from the initial brush.